What if our whole idea of intelligence, even the smartest AI we have now, is just like scratching the surface?
Hmm.
Could there be some kind of fundamental theory, like a universal blueprint for rational thinking that works anywhere, anytime?
Yeah, that's the big question.
Okay, let's dive into that because today we're really getting into the weeds with universal artificial intelligence, UAI.
Exactly. This isn't about AI that plays chess or writes poems. UAI is, well, it's this big theoretical push to figure out intelligence in its most general sense.
Right, the core principles.
The principles that would apply to any intelligent agent, whatever its environment looks like.
And we're not just, throwing ideas around. We've got some pretty dense material here that goes deep into the foundations. We're talking mathematics, philosophy, computer science. It's a heavy lift, intellectually speaking, looking at what it really means to be rational.
Yeah, and what's great about the source material is it tackles these huge questions directly. It explores the elegance of the theory, the maths behind it.
But also the practical side, even if it's still mostly theory.
Exactly. Considers where this could lead, potentially.
Okay, so our goal for this deep dive, we want to pull out the key ideas from all this complex stuff, give you a solid feel for these advanced AI concepts without, needing a PhD in maths.
Right. Aiming for those aha moments.
Yeah, hopefully you'll get some surprising insights, a wider view on AI maybe. So, intelligence. Where do you even start defining something like that? It seems huge.
Oh, it is. That's like the first hurdle. The source material points out there are, get this, over 70 different definitions of intelligence floating around.
70, wow. Okay, that really shows the scale of the challenge UAI is taking on.
It really does.
So is the idea to kind of unify these or move beyond them to something more fundamental? How have people usually tried to define it?
Well, a lot of definitions focus on human abilities, right? Learning, solving problems, understanding language, being creative, that sort of thing.
It's stuff we do.
Yeah. But UAI research often draws a line between that and what they call rational intelligence,
Rational intelligence.
which is more about doing the thought right thing, making the optimal decision in a given situation, whether or not it looks like how a human thinks.
Doing the thought right thing. I like that.
Yeah,
It's less about copying us and more about, well, getting the best results.
precisely.
So is the big goal for UAI then to land on one single formal definition of this general rational intelligence?
That's exactly how the material frames it, to develop a rigorous mathematical theory, and importantly, a parameter-free one.
Parameter-free,
Yeah.
meaning it works universally, not tied to specific settings or algorithms.
That's the ambition, yeah. Something truly general.
Okay, so how does UAI actually picture this rational agent? How does it think about it interacting with its world?
Fundamentally, UAI is described as a sequential decision theory.
Okay.
You've got a rational agent operating in an environment that's uncertain. It has to make a sequence of choices, and the outcomes aren't always clear.
So it's like trying to make the best moves when you don't know all the rules or what the environment's going to throw at you next.
You got it. And the theory aims to provide the mathematical framework to guide those choices, to maximize some kind of long-term goal or reward.
Makes sense. And you mentioned it draws on lots of fields.
Oh, absolutely. The source really stresses how interdisciplinary it is. It's pulling from computer science, engineering, economics, math, psychology, even philosophy. It's a real melting pot.
Which seems necessary given how broad the topic is.
Yeah.
Okay, so how does this UAI idea relate to things people might be more familiar with, like, say, machine learning
Yeah,
or reinforcement learning?
that's a good question. The material makes it clear UAI is kind of an umbrella. It covers all types of reinforcement learning problems.
All types.
Yeah, including situations where things are random or stochastic, where the agent doesn't know the environment's rules, and where the data isn't necessarily independent and identically distributed, IID, as they say.
So more complex, messy, real-world type scenarios.
Exactly. Situations where outcomes aren't certain, information is incomplete, and things change over time. UAI even covers standard AI planning problems that are usually seen as deterministic.
How's that different from, say, typical machine learning?
Well, a lot of statistical ML focuses on things like classification or prediction, using data that is mostly IID. UAI is aiming for a much, much broader theoretical scope.
Okay, got it. UAI is the big picture. So what are the key ingredients? What are the core theoretical ideas holding this whole structure up?
There are a few really fundamental concepts. One of the big ones is Occam's razor.
The simplest explanation is usually the best one.
Right. The source even brings up the Guru-Emerald paradox to show why we need something like Occam's razor.
Remind me of that one.
It's the idea that all emeralds observed so far are green. That's simple. But you could also hypothesize they're grew green until, say, the year 2050, then blue. It fits the data perfectly now.
But it's way more complicated and seems less likely.
Exactly. Without a bias towards simplicity, you end up with these weird, overly complex theories that still fit the past data. Occam's razor helps us filter.
Okay, so simplicity matters. How does UAI make that concrete? How does it measure simplicity?
Through something called description length, which is tied very closely to Kolmogorov complexity.
Kolmogorov complexity. Sounds technical.
It is a bit, but the core idea is intuitive. Think about it. The simpler something is, the shorter the instructions, or the shorter the computer program you'd need to describe it.
Okay.
Kolmogorov complexity is formally the length of the shortest possible program that can generate a specific piece of information, like a string of data, on a universal Turing machine.
Turing machines. Wow, we're really going back to basics here.
We are. It's foundational stuff.
So the shorter the program, the lower the Kolmogorov complexity, the simpler, and therefore the better the explanation or prediction.
That's the core idea. It's crucial for prediction. A simple model that explains the past well is generally more trusted for the future.
Makes sense.
And then you also bring in probability theory, specifically Bayesian methods.
Bayesian. That's about updating beliefs based on new evidence, right?
Exactly. You start with some prior beliefs, and as you see more data, you adjust those beliefs mathematically.
How does that fit with the universal approach?
Well, this leads directly to something called Solomonoff induction. The source presents this as a kind of universal prediction method.
Solomonoff induction.
Yeah, Solomonoff basically fused Occam's razor favoring simplicity with another idea, considering all possible theories that fit the data. And he did it using Bayesian probability.
So hang on. Instead of picking just one theory, he considers all of them.
All computable theories, yes. But crucially, he assigns more weight, more prior probability to the simpler ones.
And simplicity is measured by?
Kolmogorov complexity again. Shorter description length means higher initial probability. This gives you what's called a universal a priori probability distribution, often called M. It's inherently biased towards simplicity from the start.
Wow. Okay, so Solomonoff gives you this ultimate prediction machine by blending all possible explanations, weighted by simplicity.
That's a good way to think about it.
So how does this universal prior, this M, lead to an actual intelligent agent?
Solomonoff's work is the foundation for AIXI. AIXI is presented as the theoretical optimal rational agent.
AIXI, the optimal agent.
In theory, yes. It essentially uses Solomonoff's universal mixture of predictions to look ahead, see what's likely to happen for every possible action it could take, and then chooses the action expected to lead to the best long-term outcome or reward.
So AIXI is the ideal rational decision maker within this UAI framework.
That's the concept. It's mathematically defined, it's rigorous, but there's a catch.
Uh-oh. What's the catch?
It's non-computable.
Non-computable, meaning we can't actually run it, ever.
Not directly as defined, no. Calculating Kolmogorov complexity perfectly and summing over infinitely many programs. It's mathematically sound, but not physically possible with current computation models. The source is clear that most AI problems can be framed within AIXI, but you can't just boot it up.
Okay, that seems like a pretty major roadblock. If the perfect agent is impossible to compute, what's the point? Where does the research go?
Oh, yeah, it's a huge challenge. So the focus shifts to finding ways to approximate AIXI. To get as close as possible within practical limits.
Approximations. Okay.
Yeah.
Like what?
The source mentions a few approaches. There's things like Levin search, which is theoretically the fastest way to solve certain optimization problems. There's fast purg, another theoretically fast algorithm.
Faster ways to search through the possibilities?
Sort of. And then there are more direct approximations of AIXI itself, like AIXAO, that's AIXI, with a time limit imposed on its calculations.
Okay, making it practical by cutting it off.
Exactly. Or MCAIXI-CTW, which uses Monte Carlo methods, random sampling, and something called context tree weighting to estimate the AIXI value.
So these are all different tricks and techniques to try and capture the essence of AIXII, but in a way that can actually run on a computer.
That's the goal, and they have been applied, you know. The source mentions using these approximations for things like solving mazes, playing games like Pac-Man or poker, even some basic robotics tasks.
Really? So these abstract ideas do have some connection to tangible problems.
Yes, even if they're simplified scenarios. It shows the principles can be operationalized to some extent.
Okay, this is fascinating stuff. Now, the outline also mentioned a universal similarity metric. That sounds intriguing. How does that connect?
Right, this is another really elegant idea stemming from the same roots. It uses compression, again, related to Kolmogorov complexity and a principle called minimum description length, or MDL.
Compression, like zipping a file.
Exactly like that. The idea is you can define a universal measure of how similar any two objects are. Text files, DNA sequences, music pieces, whatever, based on how well they compress together.
Wait, how does that work?
The more similar two things are, the more redundancy there is between them. So if you try to compress them combined, you should get a much smaller result than compressing them separately and adding the sizes. The better the compression, the more similar they are.
So it finds shared patterns automatically.
Precisely. And the kicker is, it requires zero domain knowledge. You don't need to tell it anything about genes or music theory.
No way.
Yes. The source gives some amazing examples, using this compression-based similarity to build evolutionary trees for mammals and viruses just from their genomic sequences. Or classifying file types, telling a PDF from a JPEG just by how they compress, even classifying music by composer.
Just based on the raw data and how compressible it is? That's kind of mind-blowing.
It really is. It suggests that maybe a core part of intelligence isn't about specific knowledge, but about finding the underlying structure and patterns in information itself.
Wow, okay. So this links back to prediction too, right? Like sequence prediction.
Definitely. It all ties together. How do you predict the next thing in a sequence, like the next word in a sentence, or the next day's weather, when you don't know the underlying process generating it?
Right. How does UAI handle that?
Again, it uses Bayesian ideas. It considers a weighted average or mixture of all possible computable environments that could be generating the sequence.
Weighted by.
Weighted by Solomonov's universal prior. The simpler environments get more weight.
So it starts with a bias towards simplicity, and then updates based on the data it sees.
Exactly. And the theory shows that these Bayesian predictions converge towards the true underlying pattern over time. Agents like AIXR, using this universal predictor, are considered optimal in this sense. They learn as quickly as possible from the data.
So it's constantly learning, adapting its model of the world without needing explicit instructions about the rules.
That's the core concept. The UAI framework allows you to think about agents that can potentially tackle a huge range of AI tasks, sequence prediction like stock markets, strategic games like chess, complex optimization, even supervised learning, all under one theoretical roof.
Aiming to be the most intelligent, unbiased agent possible.
That's the aspiration of AIXI, yes.
It all sounds incredibly powerful on paper. But, the real world, what are the big philosophical questions or practical hurdles UAI runs into?
Well, philosophically, the source touches on deep issues. The nature of induction itself, how we justify generalizing from observations, the need for a truly unified theory of AI instead of just a collection of tricks, the fundamental basis of intelligence.
Heavy stuff.
Yeah. And it also tackles common criticisms of strong AI, arguments about computability limits, consciousness, free will, the no free lunch theorem.
Ah, the no free lunch theorem. That basically says no single algorithm can be the best at everything, right? How does UAI square with that?
It's a good point. The UAI perspective acknowledges no free lunch, but argues that the universal prior, the bias towards simplicity, towards compressible environments, is actually a very reasonable bias for the kinds of structured problems we encounter in the real world.
So it's not claiming to be absolutely best on every bizarre, structureless problem imaginable.
Exactly. But it aims to be the best general-purpose approach for the kinds of environments intelligence likely operates in. It's a bias, but arguably a very useful one.
Okay, that makes sense. And practically, how close are we to building an AIXI-like system? Are we anywhere near it?
Not really close to the pure theoretical AIXI, no. The source is pretty clear there's still a massive gap between the theory and current practice.
Because of the whole non-computable thing.
That's the main barrier. Kolmogorov complexity, the universal prior, AIXI itself, they're defined mathematically but aren't directly calculable. So those approximation techniques we talked about, they're crucial, but they're still approximations.
Right. Lots of ongoing work needed to bridge that gap.
A huge amount. But having UAI as a theoretical target, like a North Star, is still incredibly valuable.
How so?
It provides a benchmark, a formal way to think about what truly general intelligence might mean, and to evaluate how current AI approaches measure up, what their limitations are.
So guides the research, even if the final destination is, well, maybe unreachable in its purest form.
Precisely. It pushes the boundaries of how we think about learning, prediction, and decision-making in AI.
Okay, wow. We have covered a lot today, from just trying to define intelligence all the way to Occam's razor, Kolmogorov, Solomonoff, the theoretical peak of AIXI, and the practical challenges.
It's a deep topic.
Definitely. If you had to boil it down, what are the absolute key takeaways you'd want listeners to hold on to from this dive into universal AI?
I think, first, the sheer ambition, aiming for a formal mathematical theory of general intelligence. Second, the critical role of simplicity, Occam's razor, formalized through Kolmogorov complexity in guiding prediction.
Right. Simplicity is a core principle.
Third, the idea of AIXI as this theoretically optimal rational agent, even if it's non-computable. And fourth, maybe most importantly for now, the huge computational hurdles that mean we rely on approximations to make progress.
The gap between theory and practice.
Exactly. It's a beautiful theory, but translating it fully is the ongoing challenge.
So AIXI gives us this powerful theoretical lens, but actually building something truly universal and practical. That journey's really just getting started, isn't it?
Absolutely.
It makes you wonder, what are the fundamental breakthroughs we still need? What are those missing pieces to really bridge that gap between this amazing theory and machines that are genuinely universally intelligent? Something to really chew on.